Okay, we want to spend a little bit of time just going back to linear systems and invertible matrices now that we've talked about what an inverse matrix is and how to find the inverse of an invertible matrix using the inversion algorithm. Let's now take a look at this theorem here, which is something we have essentially stated but not yet proved, and that is a system of linear equations has 0, 1, or infinitely many solutions. There are no other possibilities. We kind of saw that in a system with two equations and two unknowns. We can reason through that, and you can even perhaps do that with three equations, three unknowns from a just a graphical standpoint. But four equations, four unknowns, or five equations, seven unknowns, or seven equations, five unknowns, whatever it is, it gets more complicated, and it's not clear at all why it is true for such systems. But we're going to prove that now that we have done some preliminary work, and so let's talk about this. So how would this proof work? It's a rather ingenious proof. So let me go through it. I'm going to start with this. I'm going to let AX equal B be the matrix equation for a system of linear equations. So hopefully you're comfortable with that notation. We've used it several times now. A is the coefficient matrix, B is the constants. X, of course, are the is the solution or the unknowns. So either what's possible? There could be no solution. B, there could be one solution to the system. Or C, there are more than one solution. Now you might say, you're just stating what you're trying to prove. No, it's not quite the same thing, right? We have no solution, one solution, or more than one. That doesn't necessarily mean infinitely many. More than one could be two or three, but certainly these are the only possibilities. If you have a system of linear equations, either there's no solution, or you have one solution, or you have more than one solution. That covers everything, right? So I haven't stated really anything other than what's obvious. So why did I state this? Well, the proof that I want to write then is complete if we can show in case C there are infinitely many solutions. So basically, if I can show, we've got these three cases, no solution, I can show C must imply infinitely many solutions, then we've proved what we wanted to prove. And so that's what we're going to do. We're going to assume that the system AX equal B has more than one solution. Okay, so we have more than one solution, then we have at least two. So and they're distinct, right? And that's important. So I'm going to let x sub 1 and x sub 2 be distinct solutions. So they're not exactly the same solution. They satisfy this system, and I'm going to let x sub 0 be equal to the difference, if you will, subtracting these two vectors, right, which will be, of course, n by 1 column vectors, if you think about it. If A is n by n, or sorry, if A is m by n, sorry, A does not have to be a square. We don't have to have a square coefficient matrix at all. But if A is m by n, then x is n by 1. And I'll just have you note, real important here, that this new vector we created, x sub 0, is not the 0 vector. If it were the zero vector, that would mean x of 1 and x of 2 would be the same solution, but they're distinct. So there's at least one difference in the different variables, so that x of 0 is not going to be the zero vector. Okay, so that's my first thing I want you to note. And then what I want to look at is a times x of 0. Okay, so I know ax equal b is the system I'm looking for. What about a times x of 0? Well, if I replace x of 0 with x of 1 minus x of 2, right, I have this. And then I use the left distributive property here. To write that. But what is a times x1? Well, remember x1 is a solution to the system. So a times x1, what does that mean that x1 is a solution to the system? It means that a times x1 must be b, right? It must satisfy this system of equations, this matrix equation. So a times x1, this is b. And what's a times x2? Well, same thing. X of 2 is also a solution. So a times x2 is b. And b minus b is, of course, the zero vector. So what I'm showing is this new x of 0, notice, is a solution to the homogeneous system ax equals 0. Okay. Now, let k be any scalar, any real number in this case. And I want you to consider the following. I want to multiply a times this vector x of 1, which was, remember, x of 1 was one of our two distinct solutions up above here, plus k times x of 0. Okay, let's just look at this. So k is any scalar, and we've got x of 1 and x of 0, which we created. So x of 1 plus any scalar multiple of x of 0. So what is this equal to? Well, if I distribute the left distributed log, I get a times x of 1 plus a times k x of 0. And what's this? What's a times x of 1? Well, we know already x of 1 is a solution to ax equal b, so that gives me b, the constants vector. And then here, notice I can bring this k outside, because it's a scalar multiple. I can move it around. I get a times x of 0. What's a times x of 0? Well, we just did that a minute ago, right, to show that it was what? The zero vector. And what do we have then? K, any scalar multiple of the zero vector, is the zero vector. So b plus the zero vector is just b. And so what have I shown here? This vector here satisfies ax equal b. So this new vector I've created is a solution to the system. So x of 1 plus k x of 0 is also a solution to ax equal b. Now, put a comma there, right? So it's also a solution. And here's the kicker, right? Here's the clincher. Since there are, how many choices, this scalar k, how many choices are there for that scalar k? How many choices are there? K is any real number. How many real numbers are there? Infinitely many. So since there are infinitely many, choices for k, and remember that x of 0, very importantly, was not the zero vector, right? So I'm not adding, you know, this, if x of 0 was the zero vector, I would just have x of 1. That's not what I want. I want x of 1 plus something, which is not x of 1, right? So x of 1 plus something, that's not the zero vector. That's not going to be x of 1. So, and since that's the case, then what do I have? There are infinitely many different combinations I can create here. K can be any real number, and every real number I choose, I'm going to get a different vector, x of 1 plus this. But this vector, we said, is always a solution to ax equal b, and so ax equal b must have infinitely many solutions. And that's the proof. We just had to show that last case where we have more than one solution implies infinitely many solutions. And so the proof is really unique. I wouldn't expect anyone in here just to come up with this proof. No way. but I like to show you and walk through the proof. Some of you will need to know about proof, especially if you're a math major, but even if you're not, you might have to at least read through proofs. And so it's important to go through a proof and sort of see how things work. There's lots of important ideas that can be illustrated in that. And the real kicker here is just the construction of this thing, you know, that we have at least one solution, then we well, more than one solution, but we choose one of those solutions, and then we add this multiple, right, and this x of 0, which was found as the difference of two distinct real solutions, which makes it not 0. This gives us infinitely many solutions, and it turns out, right, when we plug this through, that we get this vector being a solution. And this also is an important thing also that we can talk about, where any solution to ax equal 0 is comprised of a particular solution to ax equal b and a scalar multiple of a solution to the homogeneous system, because x of 0, remember, was a solution to ax equals 0, the homogeneous solution. And so this is the proof. Hopefully that was of some benefit to you. If not, at least I can say that I have indeed proved what we have assumed, which is for any linear system of equations there are 0, 1, or infinitely many solutions.